All right, section 7, clip 2 on circles in the coordinate plane. In this clip, we're going to be focusing on 2 examples, really just different applications of the equation of a circle. So this first example, we're going to be given something similar to what we started with in the previous example in the previous clip. We start with the graph of a circle that we are then asked to pull out the equation of that circle. So just like in that example, there are 2 things that I need. Number 1, I need the center location of the circle. That's actually conveniently shown here at the coordinate point -1, +3. So I have my center. But the second thing I need is I need the size of the circle. I need the radius, the distance from the center out to the outer edge. And that's where it's a little less convenient here. In this case, you'll notice that they give me a point that's kind of diagonal to that center location at -5, 6. And they do that on purpose. It is possible to find that distance, and which will translate into a radius. Okay, so for the record, in this example, I've actually drawn the circle itself. In big ideas, they might not draw the circle. They might just show 2 points in space. Okay, so in other words, if you ignore the fact that the circle's drawn, if I just had these 2 coordinate points, and I told you that this -1, 3 was the center, then I would know that this point is just on the circle. Okay, so I could just start with a point on the circle, like -5, 6, and the center. As long as I've identified which one's which, I can find that radius. Because fundamentally, a radius is just simply the distance from the center to the outer edge. Well, if that point is on the circle, I really just need to find the distance between these 2 points. Enter the distance formula. And this is something that you have definitely done in the past. And if you don't want to have to memorize that formula, I'll make sure I write it down for you right now. So just make sure as I come across that formula, you write it in your margin somewhere so you don't have to memorize it. But essentially, that's going to be our strategy here. We already have one piece of information we need. We have the central location. We need the radius, and we can find that by simply finding the distance between the 2 points. Once we have that, we can write the equation of our circle. So let's jump to the whiteboard. All right. So again, what we start with here is a little bit different than what we started with in the previous example. We do have a starting center location. In this case, it's at the coordinate point -1, 3. Whether they explicitly tell us, like they did in that example, or they just show us a point, and we have to translate that into a coordinate point. In either case, we have our center location. That will be valued for that left-hand side of a circle equation where I need the h and the k, right? But the next piece I need is the radius. And here is where I was not told what the radius is, but I am told another point on this circle. I am given some other point, -5, +6. I write that in a different color because this is not something that will be used for what I need in the equation. I need to use this to find the element I need. Okay, so this -5, 6 will not end up in my equation. But I need this to figure out the distance between these 2 points because that distance is literally going to be the radius of my circle. So enter the distance formula. Oh, this marker's dead. I'll keep using pink. All right, so distance formula. Now, the distance between any 2 points in a coordinate grid, that tends to be expressed with a diagonal line. You're going to notice that this is, one thing I want to point out here is that the distance between these 2 points, the center and some point on the circle, is just another way of describing radius. So the distance between these 2 points is going to be the radius of this circle. And so what is this equation? This will look familiar even if it's very depressing once you see it. We get a long-ass square root. x1 minus x2 squared plus y1 minus y2 squared. So if you don't want to have that memorized, write it down somewhere in your margin right now, just so that you know what to apply. This applies to any 2 coordinate points in the coordinate universe. I can find the distance between them. Just describing really quickly where this comes from. This is essentially just another use of Pythagorean theorem. x1 minus x2 literally describes the distance horizontally, the distance from left to right between any 2 coordinate points. If I subtract each of their x components, I'm finding out how far apart they are. And no matter where they're located in the coordinate universe, this will tell me how far apart from left to right they are. y1 minus y2 will tell me how far apart up and down they are. What I'm essentially creating are legs of a right triangle. Horizontal leg, vertical leg, and notice I have horizontal leg squared plus vertical leg squared. That should give me the length of the hypotenuse squared. Well, the length of the hypotenuse is that diagonal, which in this case is going to represent the radius of that circle. And the reason I have this big ass square root is because if I am solving for the length of a hypotenuse, ultimately I'm going to have some a squared plus b squared, and I need to take the square root of it to find that c length, that hypotenuse length. So that's actually where it comes from, in case you did not know. All right, well, that lot of good that did me. Now let me get back to the actual solution to this problem. I need to find the distance between the center point, negative 1, 3, and some other point on the circle, negative 5, 6. So here is where we're going to apply a couple of labels to this. All that's really important here is that I'm just consistent with whatever my point 1 is and my point 2. It doesn't matter which one's which. If you want to make this your starting point and go distance to the center, or if you want to start with your center point and go distance to that outer point, it's actually the same math either way. All right, so let's just go ahead and say this is our starting point, our point 1. So I'm going to call this x1 and y1, which is going to force this to be x2 and y2. Right? As long as you're just consistent with the direction, it doesn't matter which one's 1 or 2. Okay? As long as an entire coordinate point is 1 and an entire coordinate point is 2. So now I'm just plugging in those values, and then it's just calculator work. All right, well, let's plug this stuff in. So r, my radius, what I'm ultimately solving for at this point is going to be the following. Square root. I'm going to take my difference of my x values squared and add it to the difference of my y values squared. I'm just plugging that stuff in. So x1 was negative 1. x2 was negative 5. I usually go through the effort of doing the minus sign twice just so I can emphasize when I need to change the sign. Some of you guys would probably do that in your head. I'm okay with that. Just make sure you don't make those mistakes, because that's one of those more common mistakes that students make anytime there's a negative involved. All right, and then my y values, I'd have 3 and 6. Just plugging the numbers in. Just be careful about your negatives. That's the most common mistake there. At this point, now I'm just doing the arithmetic. Negative 1 minus a negative 5 is the same thing as saying negative 1 plus 5. That's going to come out to be 4. 3 minus 6 is going to give me negative 3. And then the rest is going to stay the same here. Oops, wrong color. So that 4 is going to be squared. I'm going to add it to that negative 3 squared. And here's why the direction didn't matter. Because whether I get a negative or a positive, once I square it, it's going to turn positive. And this is still the radius, right? And so next thing I would do here is just do the arithmetic again. 4 squared is the same thing as 4 times 4. That's going to come out to be 16. Negative 3 squared, or negative 3 times negative 3, is going to turn positive. That's going to turn into positive 9. So when I add these two pieces together and take the square root, this one's actually going to turn into a nice friendly number. I'm going to get the square root of 25. It looks like a lot of work. I'm just showing all the steps on the in-between. None of it's really terribly complicated. And what I'm ultimately going to get here is that radius is 5 units. Be prepared, it won't always be a friendly number. Just always double check to see whether or not they're looking for something around to the nearest 10th or 100th or whatever. Okay, so in this case, again, I have 5 units for my radius. This will be super valuable for the building of my formula. So let me go back to why this was all important to begin with. So again, I need to write the equation of a circle. I have some center coordinate point. I now have my radius. So let me get rid of all this work that I did. So now that I've found out my radius to be 5 units, again, the distance between this point and some outer point on the circle, which will be the same as any other point on that circle, All right, but I have a center and I have a radius. At this point, I can literally plug right into my equation. So I'm going to have x minus some value squared plus y minus some value squared equaling to some radius squared. Just plug in those values. -1 for that x value, +3 for that y value, and then that 5 squared. Simplify it and we're done. So instead of minus and negative, I'm going to turn that into plus. So I have x plus 1 quantity squared. Y minus 3 doesn't simplify any further, so that will stay just y minus 3. And then this is an actual number. 5 squared is going to turn into 25. There is the equation of my circle. All right. So at this point, I'm done with the equation. Just to be aware that other things they could ask me at this point based on this, they might ask me to test whether or not a point exists on the circle, and we're going to do that example next. But in that case, I have this officially written out. I can check coordinate points that would be plugged in for x and y values at that point. All right, let's move on to our last example for chapter 10. So in this example, it's actually going to be a very, very similar question to start with. It's going to be like, all right, write the equation of a circle. With the exception that now, let me show you the actual question phrasing. Now I'm going to be asked to prove or disprove whether or not a coordinate point exists in this graph. And they give me a coordinate point to test. So the way I'm going to do that is I need to build an equation just like we just did. Right? And if I have to use distance formulas, so be it, but I'm going to create an equation of a circle. If I'm testing, proving, or disproving, so it's possible this does not exist on that circle, if I'm testing whether or not it's there, I'm basically plugging in these x and y values in for x and y. If the equation checks out, it exists on that graph. If it does not, then it simply doesn't. Let me show you what I mean. So let me stuff this here in the corner. All right. So I am given some information about this circle here at the very end of this question. It says it's on a circle that's centered at the origin and then contains this other point. So first off, let's deal with the two pieces of information I need. I need a center at some coordinate point, and I need the size of that circle given by some radius. When they say it's centered at the origin, just in case any of you didn't know, the origin is literally the coordinate point 0, 0. Now, the other piece of information tells me that it contains the point 2, 0. Now, at this point, I could do the distance formula. Plug it into x1 minus x2 quantity squared plus y1 minus y2 quantity squared. Take the square root of that whole mess. It's a lengthy process, but not terribly complicated. Or, in this case, it's actually a bit of a shortcut. If you think about the origin at 0, 0, and then the coordinate point 2, 0, if you actually visually think about where that would be located, this coordinate point 2, 0 is actually directly to the right, horizontally to the right of the origin. In other words, I could literally just count the boxes to this point. This goes 2 units to the right, up and down 0, meaning it's exactly 2 units away from the origin. So that one's actually a bit of a shortcut. The radius here is 2 units. And at this point, now I have everything I need to build the equation. All right, technically I would have x minus that 0 squared plus y minus that 0 squared equal to that 2 squared. That should look a little familiar to that first example that we did. And this will simplify to the following equation. X squared plus y squared equals that 2 squared, or 4. Great, there's the equation of that circle they described. But now I'm testing whether or not the following coordinate point exists on the circle. Does the square root of 2 exist on this circle? Essentially, all I'm going to do is that each of these represents an x value and a y value. If I plug x and y in here and it checks out, it makes sense, then it's on the circle. If it doesn't, it's simply not. So when I plug in that x value of square root of 2 and that y value of square root of 2, they won't always be the same number. I'm checking to see if this equation makes sense. Students get intimidated by this. These end up just canceling, the square root of 2 and 2. So this is literally going to be 2 plus 2 equals 4. Hopefully you check out that makes sense. This one